You good?
Yep, go ahead.
All right. Hello, everybody. Welcome to the first SIAM student-led summer colloquium series talk. My name is Jared Brzezinski. Today we have Abraham Flores. Abe is a fourth-year PhD student. He works for Professor Kenneth Nollett in neutron proton scattering. Abe also happens to be the president of the SIAM student chapter here at SDSU and is also currently interning at NASA Langley this summer. And he's here to talk with us about nuclear collisions from first principles. Abe?
All right. Thanks, Jared. So specifically, I'm supposed to talk to you about variational Monte Carlo calculations of neutron scattering from Tritium. So let's get into it. So ab initio calculations of nuclear collisions, that is calculations from bare nucleon-nucleon interaction. Because unbound states are quite a bit more difficult to treat than bound states, there has been few of these calculations done so far. And there's VMC and plenty of other ab initio methods have been quite successful in accurately describing bound state problems. And what we require is that we need a 2-nucleon interaction and a consistent and accurate 3-nucleon interaction and a way to solve the many-nucleon Schrodinger equation, which is what VMC gives us. We hope in the next 2 years we can finalize the methods we're developing right now for generating reliable predictions of low energy nuclear cross sections, and do it in a way that would be able to provide valuable insight for the developers of these nucleon-nucleon interactions. So just diving into the details right away. We begin with the many-nucleon Schrodinger equation plus a boundary condition, and this boundary condition is the essence of how collisions are formally described in scattering theory. Moving on to the nuclear Hamiltonian, we have the standard kinetic energy. We do account for the proton-neutron mass difference, but I've left that detail outside of the slide. And we immediately see the fundamental necessity of accurate nucleon-nucleon interactions. That is, specifically, they pop up right in the Hamiltonian. And if you can't accurately describe these or model them well, then your whole method is going to be bad. The first thing to note about the nuclear potentials is that the quantum Monte Carlo methods, and for us, variational Monte Carlo, require a potential that is diagonal in R space, that is local in coordinate space. And this is important because until recently, the chiral potentials that have been hyped up could not be used within the Monte Carlo framework. Specifically, the calculations I'll report to you today have been done with argon V18 and urbana-9, and those family of potentials have been long used with variational Monte Carlo calculations. And an important thing to note is that quantitatively accurate nucleon-nucleon potentials have only existed for about 25 years, and theorists are still trying to figure out how to compute with them in anything other than special cases, for example, light nuclei or near closed shells. Moving on to the form of our variational wave function, we start with an antisymmetric translation invariant single particle wave function. And the power of this variational wave function, although it might be more complex than what something you're more used to seeing, is that the central correlations keep the nucleons at a favorable pair separation because we don't want our nucleons to sit on top of each other. And this provides the appropriate repulsion. The correlation operators are built to mimic the influence of the two-body interaction, that is the interaction of the nucleon-nucleon interaction. And this variational wave function gives us the ability to construct clusterized or asymptotically correct trial wave function. And that clusterized wave function is important, as we'll see later. Now, bringing it all together, into the variational Monte Carlo framework, the goal is to minimize the trial energy that is based off of the variational principle. We compute the energy through these high dimensional integrals, or we're evaluating the Hamiltonian, simply stating that it'll always be less than or equal to the true ground state energy. And the main cost is that these integrals have to be computed through Monte Carlo methods. The result is that VMC is evaluating a realistic Hamiltonian at about 3 to 4% of the experimentally observed energy. With more sophisticated techniques, you can get it down to about 1 to 2%. Now, on a more computational note, we construct the wave function as a spin isospin vector, which currently results in VMC topping out around carbon 14, where I've listed up to carbon 12. And these calculations are done on leadership supercomputers. Most of the VMC calculations that Robert Waringa has done has been on Argonne supercomputers. So now that we have our variational wave function, I'd like to give you a brief introduction to scattering. So we start with some monochromatic source. It can be from whatever you want it to be. For us, it's a neutron beam. The culminator will narrow that beam, so you get particles aligned, hits the target, and then it'll scatter, or maybe it won't scatter. That'll be important in the next slide. But your detector will pick up some amount of scattered density, and in relation to a solid angle. And this will allow you to compute the total cross-section of the reaction. Now that the beam that doesn't get scattered is obviously still there. So we have the scattered wave function, which can be represented as a decaying plane wave with some angular dependence. And that angular dependence is the scattering amplitude, that is f of theta and phi. And we find that we can compute the scattering. If we can compute the scattering amplitude, we can directly compute the differential cross-section, and that is trivially the total, will give us the total cross-section of the reaction. So now we move on to computing the scattering amplitude. First, we have to introduce some basic quantum mechanics. We just do our usual partial wave expansion with various caveats, and we separate out the radial and angular dependence, and a convenient parameterization of the scattering amplitude. We find the following relation to the phase shift. So now we have a computational goal to compute the phase shift. Now that boundary condition I was talking about. So now we need, requiring that a radial solution and its derivative for the partial waves be continuous throughout all of space. We find the following boundary condition, but we can't forget about Coulomb, because the electrostatic potential between the two particles, the target and the source, that is infinite. That 1 over r in the Coulomb potential doesn't go away ever. And the solution to that radial Coulomb Schrodinger equation, that is the radial Schrodinger equation with just the Coulomb potential, we have the Coulomb wave functions f and g, where f is the regular solution, g is the irregular solution, and we have u as a linear combination of them, and a and b are simply amplitudes, and what we will find is that they will determine the scattering matrix, that is the entire properties of the reaction will be baked into the scattering matrix, which are determined by the a and b coefficients. And this logarithmic derivative boundary condition will be the core idea of how we incorporate scattering into VMC. But some terminology first. In nuclear reaction theory, we can have a combination of all of the target and source, that's simply called the partition. But more importantly, each of those partitions are distinguished by a state of excitation of each nucleus, and such pair of states is known as a reaction channel. For example, we have, in our case, we have neutron plus triton, but that doesn't have a breakup, so it's not obvious what's actually happening in the channels. So the excitation is what is determining our channels, and that is determined by our partial waves. As we can see, our partial waves are made up of spin and L, coupled to some total J, and so we will have channels of J with a specific parity. So moving on to computing the phase shift, which is a core idea of the scattering matrix. So translating that incident plus scattered wave function boundary condition that we saw at the beginning into formal theory, we have incoming and outgoing waves whose amplitudes are related through the scattering matrix. They are not simply, the alpha and beta do not simply translate one-to-one to A and B, but they are very easily related, as we will see in the single channel case. That is, there's only one open channel for the reaction to proceed. And with some simple algebra, we can see that A and B directly compute the phase shift and thus the scattering amplitude, and therefore we can easily compute the total cross-section of the reaction. So all we have to do is find A and B. So the more difficult part is when there are multiple open channels for the reaction to proceed. That is, with some additional and more involved algebra, we can recover the relationship between the scattering matrix and those A and B amplitudes. The difficult part of doing this is having those linearly independent solutions, that is, solutions to the many nucleon Schrödinger equation with the same projectile energy, but with different logarithmic boundary conditions, which is quite a problem for the ab initio methods. So moving away from the theory for a moment, we are computing neutron triton scattering as a test case because it presents the first non-trivial case of nuclear scattering where we have all of the relevant physics. Well, besides Coulomb, because that neutron is neutrally charged, so we don't have to worry about it, but our methods incorporate it as if it was, it didn't matter. We also have available computations to provide meaningful insight if something is wrong. There was a benchmark paper done in 2011 where we have 3 different methods. We have the AGS, hyperspherical harmonics, Fadeev-Yakubowski. Those are all very good. And so it's important for us to match them with the specific potentials they used and see if we can obtain similar results and use it as a bug fitting for our methods. So specifically how we're adapting VMC for nuclear collisions is we run our VMC in a particle in a box. We don't let the Triton cluster and the neutron get separated outside 9 Fermi so that RTN can never be larger than 9. And then we enforce our logarithmic derivative boundary condition on the surface. And there are 2 different methods that we are developing in order to compute scattering. The direct method, which gets its name from the relationship between the boundary condition plus the minimized energy, which is directly computes the phase shift. And once we can do that, we then can compute separate wave functions for various boundary conditions and map out the scattering probabilities as a function of minimized energies. This is trivial for the single channel case because we can just do one boundary condition, compute the energy, get the phase shift for the direct. However, it turns out that for the other method we're developing, there was something that wasn't obvious at the beginning. We could still do that same method of computing one boundary condition, getting an energy, computing the phase shift. But what we found is that we can change a single parameter in our integral and completely map out the phase shift relationship of the projectile energy with a single optimized wave function. For coupled channels, it's a little more complicated because you need those linearly independent solutions. With the direct method, it's more involved. You now need to compute the radial solution and its derivative. And then you're able to obtain the alpha matrix that determines the scattering matrix. In the integral method, you directly compute A and B for each of the channels, and that gets you the alpha matrix exactly, and then that easily allows you to get the scattering matrix. Now, in more detail, the direct method for coupled channels computes this special kind of off-diagonal matrix element. So it's special because the left wave function on the side is a clusterized wave function. That is, it's the cluster of the Triton and Neutron. And on the right, we obviously have our full four-body wave function. And then we're computing this matrix element. It's related to the spectroscopic factor because if that over R was R squared, the norm of that matrix element would then be the spectroscopic factor. The problem is with this is that we have to evaluate this matrix element at the surface in order to determine the scattering properties. But the variational ensemble is only performs well when our nucleons are close together because VMC is a powerful short range technique. The integral method has been, we are developing computes the asymptotic normalization constants where A and B are those A and C's. Then specifically, we integrate over the entire box. It may not be obvious, but we can compute that A from the same machinery of the asymptotic normalization constant with a regularizer on the irregular function of the Coulomb wave function G. It's important because the G diverges at the origin, which is quite the mathematical problem, but more detailed than I need to provide. Specifically, A and B get computed from A tilde, B tilde. And what's powerful about this technique is that we not only bake in information about the potential into the variational wave function, but the U relative encodes information about the nucleon-nucleon interaction. Not only that, we are engulfing information from all over the box, not just at the surface. So the powerful short range technique of VMC gets completely exploited and for our benefit. So here's the computed radial solution, U, plotted against the separation between the neutron and Triton. The aim of this figure to verify the integral method is to show you that the short range part of U is agreed upon between the two methods, that is between 0 and 4. For me, the dotted line matches roughly around where the lightish blue around 3 ECM, so center of mass energy, or it can just be referred to as the projectile energy, sits. The matching between those two lines represents that our methods are in good agreement because VMC, again, is a powerful short range technique. So we should have an agreement between those two. Now, I love this figure because it shows the computational power of the integral method because these overlaps are computed using a single optimized wave function. So we get all of this information from a single source. Moving on to using these methods to compute phase shifts. We see on the left, we have the S wave single channel, and then on the right we have the 0- P wave. And so immediately we see on the left that the computational methods are comparable, and that the difference between the red and green dots for the integral method are specifically the types of potential, or the potentials we're using. So the green dots, can't see them on the left because the three-body interaction does not really have much of an impact. That is, the orange is the inclusion of the Urbana-9 three-body interaction. The red squares are the direct method. The x-axis here is the projectile energy, and the solid black curve is what we are using as our experimental results, but it really just a very, very good fit to experimental results. That is the phenomenological R matrix. On the right side, we see not only is the computational power of the integral method more advantageous, we also see the increased accuracy as substantial in the P wave. Something that to note is that a property of these figures is a constant log derivative boundary condition. That is, u prime over, if u prime over u is held constant, those lines are diagonal on this figure. So the mess with the red squares on the right is just exactly the pathology you would get from a variational method that can't give you down to the correct ground state of the box. Next up, we have our first coupled channeled reaction. Although it is a weak coupling between S and D wave, we know it's weak because the mixing parameter seen in the subfigure on the right side, which the mixing parameter is a representation of the ratio between the partial waves. And as we can see from the small mixing parameter, this implies that the channel is not mixed and is dominated by a channel. In this case, it is dominated by the S wave on the left. We have not computed the direct method for this channel simply because it was not computationally obvious for me currently, and it was more involved, and we were currently working through the integral method details. But as you can see, the integral method is quite powerful. So moving on to the 1- channel, and this is a case of spin mixing, we see that the channel is strongly coupled. This is the large mixing parameter tells us that, where we have roughly equal ratio, or equal amount of each partial wave. Here we have computed through the integral method. Again, the strong coupling resulted in not obvious how to compute through the direct method. And something to note is that these results are relatively fresh and then are still being worked on, simply because the reported error bars are not probably not 100% accurate. They're still working through that, and it is not obvious the method of generating the wave functions that go into these. There are quite a few techniques that still need to be investigated. So in summary, we have developed two methods for extracting scattering information from wave functions that play, and specifically the integral method plays more to our strengths of our computational approach by focusing on the wave function interior and takes advantage of some cancellation of errors. Once I get done with my internship, we're moving toward publication once we can examine all of the angular momentum states we want, compute results for all nucleon-nucleon interactions. And the final note I want to end on is that the essence of the integral method is very, very close to using the VMC solution as a trial function in the Lippmann-Schwinger equation, where the Lippmann-Schwinger equation is just the Schrodinger equation recast as an integral equation suitable for imposing scattering boundary conditions. So the formal techniques of that have been developed for quite some time. And in the path ahead, the integral method will hopefully be more important for Green's function Monte Carlo, because this is important because Green's function will simply sample out and not be able, the difficulty part would be the integrals are more easy to compute rather than the surface radial solution. And with that, I would like to thank you for your time.
Thank you, Abe. Appreciate it. Does anybody have any questions for Abe?
I have a question.
Yes.
Okay. I'm familiar with something called integral methods, but I don't know if this is the same. So to me, it's maybe it's the way you call it there. But when you basically you're doing an integral, and that's what it's called integral method. And when that is direct, what do you solve the PDE?
So these are just names that we call them because it just seemed an easy way for us to differentiate and talk about them to other people.
Yeah, I would say that this is not a broadly standard terminology across nuclear physics. This is just sort of the handful of us who've been doing these things have called this way of extracting information out of a wave function the integral method. But it doesn't, as far as I know, connect as a language thing to anything else that anyone does.
Okay, thanks.
Yeah, Calvin, do you have a question?
Do you have any ideas how hard it will be to scale up to larger systems? I mean, this, like you said, this is the smallest non-trivial case.
Yeah, so I did have that. So yeah, so roughly carbon-12 would be like the highest we would want to go. Those calculations would be done on a supercomputer, and I imagine we could still do them, but it would be quite a long ways down the road, like 2 to 3 years. Yeah, we would definitely.
Right, but what about some of these intermediate ones? You know, lithium or something like that.
Oh yeah,
Is that tractable?
Yeah,
you know,
I think so. I think so, and probably about a year or two once we refine these methods in the helium 5 and hydrogen 4, it'll be, I think, very easily extended to lithium 7.
Yeah, I would say we're basically this all when it comes downstream of doing the same thing that we've always done with VMC and Green's function Monte Carlo, in that you get a wave function, and then this is an integral over a wave function, just like any matrix element. And what Abe has found is that you can go a long way with not even finding a different solution at each energy, but you sort of find an energy sort of 3 MeV-ish, and then you can just sort of by doing different, cranking through slightly different integrals on the same wave function, you can get phase shifts over in 6 or 10 MeV range. So it's kind of the same as the same answer as any matrix element you would want to get out of these methods.
to add on that, I think that specific energy, right, that single energy, it would be reaction dependent. I think that three MeV is probably related to the structure of the cross section for neutron off Triton.
Yeah, though, I mean, you know, right, the masses aren't all that different. The energy scales aren't all that different. So it's probably not that different. It's probably not that different from one case to another.
I see. Rodrigo, did you have a hand?
Yeah, I was just curious. Have you looked into how dependent it is on the interaction that you're using? Like you listed AV18 and the Norfolk potentials and CD1.
That's as soon as I get back from working from NASA, that's what I'm computing.
Oh, great. Sounds good. Yeah, it'd be interesting to know if what is the biggest source of the uncertainties. Is it from the wave functions? Is it from the interaction? Is it from the method that we're using?
Yes, yeah, I'm very, very excited to see those when I get them done.
That sounds great.
Do you have another question, Kelvin?
No, sorry, I just forgot to lower my hand. Let me try to, oops, wait, nope, lower hand.
Suppose if there's no more questions, then I guess that about wraps it up.
Yeah. I would like to make one comment though, which is that you know, this business of these phase shifts that you get, that you know, they look pretty comparable to, you know, what people get out of the you know, Fadeev like sort of things. Yeah, like, you know, this thing on the right here where there's the, you know, there's the direct VMC and in those red squares. I didn't really think I would ever get anything better than that out of VMC, and then it turns out that it looks like you take the same, basically the same wave functions, but you have this more intelligent way of fishing the phase shifts out of them. And okay, so we don't know that Los Alamos fit in black there is the correct thing, but this is certainly suggestive of the VMC, you know, even just the VMC level, not going to GFMC, you know, we can get a lot of useful information about cross sections this way. Sorry, don't mean to derail you, but felt like that needed some emphasis.
No, I think that's
no. It really is a big improvement from, and like you said, like it's hard to know if you know, the phenomenological R matrix is the real one, but it's the one that is based the most on the experimental data. So I think it seems to be going in the right direction.
Yeah, and this also, right, so the previous sort of most extensive batch of calculations that were done this way were these neutron scatterings on helium-4 that I did a long time ago. And so this business on the right where you go from the direct VMC that kind of looks like there's something wonky with it to this thing that's in, it seems to be a nice agreement with experimental constraints. Like, you know, in order to do that, I had to take my VMC wave functions and put them through Green's function Monte Carlo, and then the Green's function Monte Carlo would give me the nice agreement with the experiment. But the fact that you can just use the variational trial functions in this way that you know, it looks like there was better precision hiding in there that was just waiting to have some way found of fishing it out.
I was going to say it would be, for those of us who are slow learners, it would be interesting to sort of see this done in detail in a more toy model, just one-dimensional potential scattering, to see how this works. You know, particularly the fact that you can use just essentially one trial wave function and then get the other stuff out. That would be, or if you could give me some hints of how to do that, I would be at some point when time is available. Or
I do have some toy code that could be probably, where I used the argon V14 potential, which is very easy to code up.
Yeah, I was just thinking of something even simpler, just, you know, how the integral method could be used, which is simple potential scattering, and show how you can get out lots of phase shifts easily or something like that. Does that make sense?
Yeah, no, I think that would be a very, very good idea.
This just sort of illustrates the fundamental idea before you put in all of the the important VMC
Yeah.
machinery.
Yeah, I think doing that, I think would have probably helped me a lot these last 2 years before it. So
Yeah,
I think that's a good idea.
I'm slow, so I have to start with the simple picture first.
Did you have anything else to say, Ken? Or
I don't think so. I mean, I agree. I agree with Calvin. I mean, I think in our, in my head, the way this went was that I did some version of that when I was doing bound state ANCs along, right, in the lead up to doing the bound state, doing the bound state bound state asymptotic normalizations from VMC, and then this is sort of downstream from that in my head. But obviously, what happened in my head didn't happen in everyone's.
Well, I guess on that note, I would like to thank everybody for coming today, and invite everybody to next week's talk, where Eric Medvedev, my friend, will be giving a talk on his research. I hope to see you then.
Thanks, Abe.
All right.
Thanks
Thank
for the
you.
talk.
Thank you. Great talk.
Take care.